Thank you for attending today's SEL webinar. Before we start, I would like to bring a few items to your attention. This is an audio-only broadcast. All participants are muted. Today's webinar will be 60 minutes long with time for questions and answers. There will be a recording which will be available on our website as soon as possible. If you have any questions throughout the presentation, please submit them to all panelists with the Q&A tool at the bottom right-hand corner. Any questions that are not addressed during the live event and the Q&A session will be answered by our experts personally via email. Our presenter today is Gianfranco Patti from SEL. Gianfranco specializes in distribution and transmission systems. He was involved on design, construction, and operation of power systems in Colombia, specifically for oil fields and generation plants. In 2018, he joined SEL as an application engineer, where he has had the chance to expand his knowledge, particularly in protection and control systems. During today's webinar, we will discuss alpha plane and its benefits in line differential protection. I will pass the microphone to Gianfranco.
Hi, everyone. Thank you, Mariam, for the introduction. First, I would like to thank everyone for taking the time to join the webinar. My name is Gianfranco Patti. I'm an application engineer for almost 5 years now for SEL here in Spain. And we'll be talking about the line differential protection, particularly the SEL patented operating characteristic called the alpha plane. So let's begin. First, let's talk about the general concept of a differential protection for any element on the power system. We'll have a protected zone that will be defined by the position of the CT around it, like we can see here. So basically, what we try to do is calculate a differential current that will be the summation, the phasor summation of the currents entering and exiting the protected zone. So let's see what happens when we have no fault in the system. We have a regular load current, which is a current entering the protected zone in the left. And ideally, that same current is going to be exiting the protected zone at the right. In that case, as the current in the left is entering the CT in the polarity and is exiting the CT on the right by the non-polarity, when we do the phasor summation of those currents, it should be something close to zero. So we have no differential current in that case, which means no fault. But when we have a fault inside the protected zone, that current is going to be entering on the left, as the same as before, but right now we'll have a current entering also in the right side of the protected zone on the polarity also, and that phasor summation will give a result different than zero, which will mean that we have a fault on the protected zone. So normally this can be done by one relay if we are protecting, for example, a transformer or a bus bar. Because the CTs delimiting the protected zone are on the same environment, the same substation. Okay. But when we're talking about differential protection for lines, each terminal of the line will be separated by a distance, which can be a large distance. So in differential schemes for lines, we will have two relays, as you can see in the image. And we'll need to place a communications channel for them to communicate the current information from both terminals. This introduces some challenges. For example, we'll need to have a dedicated bandwidth for that communication. They'll be exchanging continually phases and sequence currents. So there needs to be a constant exchange of information. And this information needs to be aligned in time because, as you can imagine, the communication channel brings a delay Okay, the communication is not instantaneous, and both relays also have their own processing time. So we'll need to take care of the alignment of those currents. And also, now the protection scheme is subject to channel availability and misbehavior. Okay, this is something that now that we have two relays and a communication channel, that this can affect the protection scheme. Besides that, we also have to take into consideration what happens when one of the CT saturates. Also, the phenomena of line charging currents, and what happens when they have transformers inside this protection zone, this transmission line. Okay, we'll take care of all these points through the presentation. So let's see. What is the alpha plane? Here we have the same theme we were seeing before with the two relays and a communication channel. And the alpha plane is simply a way to draw an operation region. And we first calculate the operation point, named K in this case, just divided the phasors of the local current and the remote current. And we plot that result, that operating point, in the alpha plane, which is an imaginary and real, as you can see here on the down on the right, an imaginary plane. Okay, as simple as that. So let's see some different scenarios of typical scenarios of our system and how this operation point behaves for these different scenarios. So here we have the base scenario, load current. We have no fault, just current flowing through the line. Here we can see the local current. As we were seeing before, this current that enters on one side of the line is going to exit on the other side of the line, but with a different polarity. So that will plot in the -1 on the alpha plane. Okay, this is just this is called the ideal blocking operation point, okay, of the alpha plane. This is the standard state of the line. But some other things can happen because we have a communication channel. We can have synchronization errors in that communications channel when, due to the delay on the communication, the remote current is going to be received with a time delay and will plot with a slight change in the angle. Okay, so when we have synchronization errors, we can see that the operation point is going to be moving more or less around this circle here due to synchronization errors. We are still not talking about faults or anything. This is just because synchronization errors. We can also have CT saturation, as we were seeing before. We have the local current, and let's assume that the remote current, the CT on the remote end, saturates. And in that case, what happens is that the current that is going to be measured by that relay can be changed not only in angle, but also decreasing magnitude, typically. So the operation point is going to be moving in this part of the alpha plane. Now, what happens if we have an internal fault? If we have an internal fault, as we saw before, we have a local current, and the remote current is going to be on the with the more or less the same angle, okay? And that will plot on the right side of the alpha plane, as we see here in the image. Another possible scenario, which is not so common, but it also can happen, is this system we're seeing here, where we have the left part of the system is a strong system, and the right side is just load. If we have this is what we can call a weak terminal, the right side of the system. If we have a fault in the line, mostly if it's a high impedance fault, we can still have the scenario of the fault being internal, but there's still current flowing outside of the protected zone. on the right part of the line. So double plot, here we have the local current and the remote current. We'll plot with also with an angle on the other side of the in respect to the local current. So double plot, as we can see here, is still on the left part of the alpha plane, but here just typically these are small values. So based on this scenario, that the typical scenarios that the transmission line here faces, SEL has defined the alpha plane in which is what we can see here, where we have the ideal blocking point. We saw that this was the point where we have just regular load current. Okay. We saw that the internal faults will fall in the right side of the alpha plane. So this is what's inside this operation zone is restrained. So the relay does not operate if the operation point is inside. But if it's outside, will operate for internal faults in this case. But if we have synchronization errors, we saw that this will be the region of operation if we have synchronization errors, and the characteristic will allow us to restrain, to not operate for this scenario because this is not a fault. Also, the desaturation will fall inside the restraint area. You can see here. And lastly, the internal faults without fit will fall outside the characteristic here. Okay. So to build the alpha plane characteristic, or better to define it, we have an angle, which is this angle of this semicircle, and the radius of the characteristic. We will see that this gives us greater immunity to synchronization error and desaturation, as we are seeing. It has high-speed operation with times less than 30 milliseconds, more or less 1.5 power cycles. We would see at the end of the presentation some slides with operating times. And this provides for the person that is testing and analyzing the element, the differential element, with it's more easier to test because in this case we can manipulate with the regular test set the angles and the magnitudes of the currents we are injected, which are directly reflected on the alpha plane. Let's do a bit of a comparison to the traditional differential, which is the slope characteristic we have here on the right, where the upper part of the region is the operate zone and the lower part is the restraint zone. And we also have a minimum quantity of differential current to operate. These two, how do they correlate to each other? That's what we're going to see in the next slide. So doing mathematical manipulations of the traditional differential element, we can plot that slope into the alpha plane, and we'll see that translation into the alpha plane will end up in a circle in the alpha plane. Okay, so this is more or less the correlation. And here you can start to see that, of course, it's going to behave differently. There are some parts, at least here in this example, that are not covered by the traditional characteristic. Okay, so if we have a point here or here, the traditional characteristic will operate. Meanwhile, the alpha plane characteristic will restrain. So we start to see some differences here. Let's look at another example. Let's assume we have this alpha plane characteristic, okay? And that for this particular line, we have this possible CT saturation scenario and this possible scenario for CT channel asymmetry, okay? Synchronization errors. So with this traditional characteristic, we'll be mistripping in some cases due to CT saturation or synchronization errors. What if we wanted to cover those points with the traditional characteristic? We can do that. We can expand the traditional characteristic, which will translate into increasing the slope of the traditional characteristic. If we do that, we obtain the image on the right, where we are covering those cases we saw before of the CT saturation and the synchronization errors. But look at this. Remember the faults with outfit that can be here? In this system on the right, if we have a fault with outfit, it may not be seen by the traditional characteristic. So this is telling us about the compromise we have to do when choosing the slope of the traditional characteristic between these two or three scenarios. Okay. So let's take it one step further. Let's assume we expect high synchronization errors from our system, from our communication system. So in the alpha plane characteristic would be something like this, just increasing the angle of the characteristic. Okay. So in that case, let's if we try to increase the slope of the traditional characteristic to cover or to compensate for those possible synchronization errors, we see that we will not be able to cover all the possible synchronization errors, okay? And we'll still need to increase a lot the slope and loop sensitivity, and mostly for outfit, faults with outfit, okay? So this is more or less the comparison with the traditional, the percentage differential slope characteristic. But let's take it a step further, because until the moment we are seeing that the alpha plane, the operation point, is calculated divided the local and the remote current. But what happens if we have a system or a transmission line with three terminals? How do we manage to divide a local and a remote current when we have three terminals? And in this case, each terminal has two breakers. So this is why we created the generalized alpha plane. Okay, so it's a method we use to translate a three-terminal system into an equivalent two-terminal system to be able to have an equivalent local current and remote current, so that we can implement the alpha plane in system with more than two terminals. So the first step is going to be calculating the differential and restraint current on all the protected zones, calculating an equivalent local and remote current that yield the same differential and restraint current, which are the real measured differential and restraint current on the system. And with these equivalent currents, local and remote currents, we can implement then the alpha plane. Right? So this is an equivalent of the three-terminal system taken to a two-terminal, just to be able to plot it in the alpha plane and still have the same benefits that the alpha plane offers. So when we have a multi-terminal alpha plane, we saw that if the system is reduced to an equivalent of two-terminal systems, so we can provide three phase elements, negative sequence elements, and zero sequence elements. As you can see here on the next slide, these are the phase elements, the negative sequence, and zero sequence elements. Okay, one of the points we saw, the challenges the line differential has, is the CT saturation. Okay, so what SEL has implemented is an external fault detection that will help to assess the scenarios where we have CT saturation. So for this logic to work, it must detect and flag external faults before CT saturation happens. And it must not trigger for internal faults, with or without CT saturation, okay? It's based on the restraint and differential currents, which is maybe you're familiar with this. The restraint current is the sum of all the current magnitudes, and the differential is the sum of all current phasors. Here we have the logic for the external fault detection. So take a look at the result. This is very important. It's external fault detection. It's not saying CT saturation detection, okay? Because what we are doing is just to detect that the fault is external, and based on this, we will take some actions that will help to prevent a misoperation in the case we have a CT saturation. If we have an internal fault, we'll see an increase on the restraint current and an increase in the differential current simultaneously. Okay, so at the same time, they will rise together. But if we have an external fault, ideally, if there is no CT saturation, if we have an external fault, we will see an increase on the restraint current. Okay, but additionally, if we have a CT saturation, first we will see an increase in the restraint current, and then after some time, we will have an increase in the differential current. And this differential current is due to the CT saturation. In the next slide, we're going to see this in a more graphical way to understand it. But the logic, what it does is that it compares the restraint and the differential current in the present moment in comparison with one cycle before. So what it's seeing is the increase in the restraint and the increase in the differential. So if we have an increase in the restraint current, we'll give a 1 to this AND gate. And if we have no differential increase, we will not see 1 here on the upper side of the logic. So with this NOT, it will activate after 3/16 of cycle of a power cycle. We'll declare an external fault detection, okay, which is the external fault. If the fault is internal, we'll see an increment in the differential also, and this should not be activated. This is an example of an external fault. So at the beginning, when the fault starts, there is still no CT saturation until this part. So as we expect, we are going to see an increase in the restraint current, but no change in the differential current, okay? So it's just what we saw in the logic before. But in this moment, when the CT starts to saturate, we'll see an increase in the differential current. But we already declared an external fault detection here. We were already able to declare it and take some actions, which we will describe later. In the other hand, for internal faults, we see that the restraint and the differential current, as expected, will increase simultaneously, not activating the external fault detection, okay? Even if the CT saturates, like in this case. So what do we do when we already know that this is an external fault? We take some actions that we see here. The first one is we give harmonic restraint to the phase element. A fraction of the phase restraint is added also to the sequence elements. And we will change settings. The alpha plane settings were changed to a high security mode, let's say, when we have an expanded characteristic. This can be seen here on the next slide. Okay. So in the left we have the regular characteristic, and once the external fault is detected, the settings will change automatically to the high security ones, which is normally a bigger radius and a bigger angle, okay, a blocking angle. But what about the harmonic restraint I was saying before? Let's see how that works. So in this example, we have a fault which gives this positive sequence current and this negative sequence current. But this negative sequence current is due to the distortion created by the CT saturation. So if we try to calculate the operation point of this fault, we will end up with this local and remote equivalent currents, which yield this operation point, which is 0.5 angle minus 140 degrees. which will be placed in the alpha plane around here. So what we do, because we have access to the differential and restraint current before calculating the local and remote equivalents, what we do is that we add a negative sequence current to the restraint current. And once we do that, and we calculate the local and remote current, that yields operation point, which is closer to the ideal blocking point. In this case, 0.65 angle minus 151. So this point is plotted here in the alpha plane. So as you can see, we went from here, if we take no actions at all, but if we do the harmonic restraint compensation, we end up with an operation point which is closer to the ideal blocking point. Other of the challenges we saw that the line differential can face is the line changing charging current. So when we have long lines or a high voltage cable, more than 80 kilometers of line or so, the charging current, which is a current that goes inside the line from both terminals to inside the line and dissipates through the capacitors of the line, the capacitance. This is a differential current by definition, and when lines get long, this can start to be a significant number of current. So to handle this, traditionally, you can increase the operation threshold of the differential protection, but you will also lose sensitivity by doing this. So what we do is a voltage-based algorithm, which will perform well under transient and unbalanced conditions. We'll see in detail how it's done, but basically what we do is to calculate that charging current and subtract it from the actual current that the relay is reading, okay? So the charging current calculation is based on the average line voltage. This is more accurate because each terminal subtracts a fraction of the charging current. The bandwidth is preserved because here we don't need to exchange voltages through the communication channel, okay? Because locally, we will subtract a part of the charging current in each relay. So when they share the information, this has already been subtracted from the current that is sending, okay? And it's done depending on the number of terminals, okay? So if we have a two-terminal line, each side, as in this example, each part will subtract the half of the charging current from each terminal. But if we have three terminals, each terminal will subtract a third of the charging current, of the total charging current by each terminal. So this is an example of a line without a fault. These are the A, B, and C currents, and the yellow line is the measured current without compensation. Okay, so this yellow line, most of it is charging current that is going inside the line. So that's why it's a differential current. So once we do this compensation algorithm, we will end up with the blue line, okay, which is much closer to the ideal zero we should have in a case where we are only having load flowing through the line. Okay, so we are disregarding this charging current that appears to be differential current. So this seen on the alpha plane is that we have a measured current. We do the compensation, the differential current, which is created by the charging current, is subtracted from the total, and we end up with an equivalent current which will be closer to the ideal blocking point. Okay, this will stop us from having possible misoperations due to this phenomena, and increase the sensibility of the protection, since we don't have to increase our differential threshold to let this current pass. Now let's see. Another case is we can also have transformers inside the protected zone. In this case, what the relay does is it offers a vector group and ratio compensation, also harmonic block for overexcitation, harmonic block and restraint for inrush. These are phenomena typical of the transformer. Okay, so it's built in on the line differential protection, but it doesn't mean it offers a complete transformer protection package. Okay, so we don't have an restrained airfall, for example, but for the line differential, it will take care of it and compensate for this, well, the connection of the transformer, the ratio, etc. So which line relays SEL offers, which have a alpha plane? Here on the left, we have the 400 series, which is the 411L, the most complete and robust solution for the line differential. And at the right side, we have the 311L, the 300 family, which also implements the alpha plane, but there are some features that are not available on the 311L, like, for example, the charging current compensation and the inline transformer, okay? But they do have both the alpha plane logic. In this slide, we have, you can see the average trip times in cycles, in power cycles, in function or depending on the differential current. So the lower the differential current, the longer it takes for the protection to operate, but we'll have a maximum of around 1.5 power cycles, which is around 30 milliseconds with a 50 hertz system. Okay? And of course, if the differential current is bigger, we'll have faster times of around 0.8 power cycles. Let's see also how this alpha plane logic, because this is we are talking about when we talk about the alpha plane, we talk about the operation region, but the differential element per se has some other checks to do, okay, to perform the trip. So this is the differential element implemented on the 411L. So let's go one by one. Here we have the overcurrent comparator, because we still have, even if we have the alpha plane, we still have a minimum differential current to operate. Okay, so this is the overcurrent comparator. We have the alpha plane, which is the one we have been seeing this time. We have the security switch over. This part takes care of the switching the settings of the alpha plane based on the external fault detection. On 4, we have the supervisory logic, which mainly takes care of problems in the exchange data with the other relay, problems in bad bits in the communication, for example. And at the end, we have a disturbance detection supervision logic, okay? That this is mainly made to take care of misoperations that can be done by problems in communication. So if we have a bad information exchange and we have a false differential current, the relay still has to see a disturbance locally and remotely for it to operate instantaneously. So if it sees a differential operating point in the alpha plane, but it really didn't see any disturbance in the waveforms or of voltage and current, local and remotely, it just will go through this timer here to make sure that it was a fault. Because if it was a problem in communication, normally problems in communication it's a problem of 1 or 2 packets. So it will not get to 2 complete cycles in this case. Let's see a summary of the key features of the line differential with the alpha plane. So we see we have the sensitive, negative sequence and zero sequence protection elements. We have an enhanced alpha plane with dual breaker application for 3 terminals with serial communication and up to 4 terminals if we use Ethernet communications. We saw that it's immune to asymmetrical channels. We saw we can implement the line charging current compensation and the inline transformer. We saw that it offers excellent security for the CT saturation with proper restraining in dual breaker application and external fault detection. Excellent security for channel events, mostly because of the last part I was telling you about the disturbance detection. And it also has the multi-terminal fault locating. That was it for the presentation. So now we can go to questions.
Thank you, Gianfranco. We have arrived at the Q&A portion of the event. Our panelists today are Andrea Di Tommaso and William Fernandez. Andrea is an application engineer who has worked for SEL since 2019, and William is also an application engineer who joined SEL in 2016. Our panelists will now take any questions you have. And the first question is, during an external through fault, the CTs at one terminal could saturate, while the CTs at the other terminal do not. This can produce false negative sequence current at one terminal, and essentially zero negative sequence current at the other terminal. Is this 87L2P would be okay during this event?
Okay, so this is a good point, because it's true that the negative sequence and the zero sequence elements are much more sensible, because you normally don't expect in normal conditions to have this negative or zero sequence, or at least not a big portion of those currents in the. So in this case, what helps in this case is that it detects that it's an external fault. So it will perform all the preventive actions we saw when we know that this is an external fault. Will compensate with the restraint and will expand the characteristics. Okay, so that should not be a problem to have a misoperation because of this.
And the question following that is, should we add small delay? Let's say we use SV01 equals 87L2T, SV01PU equals 5 cycles, SV01DO equals 1 cycle, so that the negative sequence 87L2T won't trip DCB instantaneously?
Yeah, I think this goes in line with the previous one. I don't know if Andrea or William can give a different point of view, but from my side, I think that in this case, the external fault detection should compensate for the possible problems this scenario may have. So it shouldn't be necessary to have a time delay on those elements.
Okay, another question. If each relay divides its local current by the remote current, does that mean the operating point will be different on both relays?
No, in this case, what the relay does is that the generalized alpha plane compares the current, the local and remote current, before computing the operation point. So what it does, it's always dividing the smallest current divided by the largest current. Okay, so they both relays will have will be symmetrical. They will have the same operating point always. Okay, so this is a common confusion that can arise when testing the devices, when you say, well, this is the local for this relay, but for the other relay, that the remote is the local. So they always perform the same calculation: the smaller current divided by the bigger current. Okay.
All right. We hope you have enjoyed today's SEL webinar. To learn more about this topic, please visit our website. If you would like to connect with Gianfranco or a local SEL expert for follow-up, please take a moment to indicate this on the form that will appear when exiting the event. Again, A recording of this presentation will be available as soon as possible. Have a wonderful day.
Thank you. Thank you, everyone.